Okay, the recording is now on. So, uh, good afternoon, everyone. Welcome to the weekly discussion session for the NPTEL course titled Physics of Nanoscale Devices. My name is Jyotishwaran. I'm a PhD student from the ECE department of IIT Roorkee. This is the session for week 10, where we shall be like this is the 11th session technically, but sorry, 10th session, where we shall be covering the contents from week 11 of the course. So before we begin, from the live attendees, do you guys have any questions or queries from the previous parts of the course?
No, sir.
No questions. Okay, all right. That is good. Okay, so in that case, we can begin today's discussion. So today we shall actually be looking at quite a few things because the contents of week 11 is actually pretty dense. A number of topics are covered in it, and the assignment also is a good mix of both numerical and conceptual questions. So I'll try to cover all the relevant details, and in addition to that, as promised in the prior weeks, I have a few papers and review articles that kind of shows some of the principles that we have been discussing here in action, at least insofar as simulated device performance goes. So, in the last part of today's discussion, I shall be focusing on those papers. They are in no way directly connected to this course, but it is just to give a flavor as to where the things that we are learning in this course are being applied. Okay, so with that, let us begin. Um, so, week 11 begins with a continuation of MOS electrostatics. So, yeah, rather than because in this just one second. I think I have not shared my screen. Let me do that quickly. Uh, yeah, so is the screen visible?
Yes, sir.
Yeah, so yes, so as I was saying, to explain the concepts of like the topics that have been covered in this week, I will need to draw a lot of figures. So rather than draw them on my own and waste too much time, I thought I will run through them in the slides. Whatever modifications I make on these slides, I will share with you in the course folder. So any modifications, anything that I write here will be made available to you in the folder. Okay. So
Yes,
let
sir.
us continue. Let us start the discussion. So the notion of mass electrostatics must have been started in like week uh, 10 itself. So the idea is we study the electrostatic effects in MOS devices to kind of understand how charge accumulation takes place in the channel. So essentially, if you look at the device in this geometry, the MOSFETs have a gate terminal G, and essentially there is also a terminal over here, that is the body or the substrate terminal, which is textbooks label it as SS. Like standard practice, this terminal is shorted with the source. So VGS is technically VGSS. I'm sure you guys are familiar with this. So if we are looking at the voltage applied across these two terminals, then we can see that this device essentially acts as a parallel plate capacitor, with the yellow region, that is the insulator, acting as a dielectric for it. So I have a metal electrode on one end, a p-type semiconductor electrode, I mean, very vaguely speaking, a p-type semiconductor electrode, and an oxide dielectric in between. So applying a voltage here at some point would lead to some charge accumulation on this end of the material, And that is essentially what aids the conduction of a current from the source to the drain. So, and this principle is pretty much true for what to say, like ballistic MOSFETs, or MOSFETs with diffusive conductance or whatever. This principle remains roughly the same. So, electrostatics, of course, is studied using the Maxwell's equations. So, the equation that we shall be using is this one, which is essentially the displacement vector. So the divergence of the displacement vector is equal to the free charge that is available in the material. So if we can find the profile of the displacement vector in this direction, then we should be able to find the charge carrier concentration in this region. So this equation, of course, can further be written as so. For the purposes of the discussion in these topics, we shall not be using V to identify the potential. We shall be using the parameter psi. So over here, I can just write that psi in general denotes the potential, and therefore minus gradient of psi will give me what will it give me? It should give me should essentially give me d times epsilon r if I'm right. Or no. It will just give me yes. It will give me d by epsilon s. Yes, d vector by epsilon s, where epsilon s is the permittivity of the semiconductor material. So the bottom line here is whatever electrostatic effects that we are studying here is actually manifested through what we might have learned previously as the concept of band bending. Like when we study MOSFET devices or the MOS capacitor, the charge inversion and the accumulation of charges in the channel is also explained through the phenomena of inversion, wherein the applied potential effectively dips the conduction band or the valence band energies correspondingly above the Fermi level, because of which we have a large accumulation of the minority charge carriers. So in the case of an N-channel MOSFET, the conduction band bends below the Fermi level and there is an accumulation of electrons. And in the case of a P-channel MOSFET, the valence band bends upwards over the Fermi level, which leads to the accumulation of holes. And it should be noted that in a like typically in a p-channel MOSFET that is operating in the depletion mode, the actual channel material is an n-type semiconductor, and in an n-channel MOSFET the actual semiconductor is a p-type material. So those are like the basics that you guys would know. Now we also have a notion of what the free charges in the material are. Like we already are aware of what the sources of the free charges are. So those are the intrinsic holes, the intrinsic electrons, the ionized donors and the ionized acceptors. This is the most generalized picture in which we assume that the semiconductor here contains both donor and acceptor atoms. So these are the free charges. Therefore, the Poisson equation, like this equation is called the Poisson equation. So the Poisson equation uh, in general can be written as this. So after this, yeah. So this part essentially tells us the electric field profile. So if we assume that the material is p doped, in which case like the dopant concentration is much higher than the intrinsic charge carrier concentration. So yeah, so I mean, before we proceed, typically for silicon at room temperature, what are the values of the intrinsic charge carrier concentrations? Can either one of you tell me? Hello. Yeah, Kamal or Chanshu, am I audible?
Yes, sir. Yes, sir.
Yeah, so can you guys tell me what is the approximate value of the intrinsic charge carrier concentration for silicon?
Actually, sir, I don't know.
Oh, you don't know? Okay. So do you know what Ni squared is approximately? Like we write the law of mass action, right? Np is equal to Ni squared.
Yes, sir.
So do you know what Ni square is approximately at room temperature? It's around 10 to the power 20. So in intrinsic silicon, okay, Chanshu dropped out. Uh, Kamal, can you hear me? Like, is these
Yes, sir. Yes, sir.
okay?
I'm
So
here.
it must have been a signal issue on his side. Although I see three attendees. Oh no, that is just me presenting. Okay, fine. So yeah, so typically it is to the order of 10 to the power 10 per centimeter cube. So in your questions, you should pay attention to these numbers also. When we are looking at some example problems, I will tell you how to handle those things. So going back.
Yes, sir.
So essentially, the Poisson equation in for a p-type material, all of these quantities Nd plus and N0 and P0 will all be very small compared to Na. Therefore, dE by dy can be directly written, and Na minus is what we have because since we have acceptor atoms, they will accept an electron, and therefore they will have a net negative charge. So that is why we write d by dy as minus q Na by uh, epsilon s. So the notion is that when we are moving along the y-axis, at some point the electric field is going to be some non-zero value, which is essentially the surface electric field. And as we are moving further and further through the material, the electric field will eventually become zero. So that is the thickness WD. So if we assume that the electric field decays linearly, which is a fair assumption because uh, like we generally assume a like how do I put this? A constant potential difference, right? When we are trying to impose a voltage across two terminals, we assume that the voltage kind of drops uniformly from terminal A to terminal B. So if the voltage drops uniformly, then not uniformly, it drops linearly, then the electric field will also show a similar trend. So using the area under this curve, we can find out what the various parameters are. So d by dy should essentially give us, yeah, so d by dy is the slope. And from the Poisson equation, we know that this is that quantity. And because of this slope, we will also be able to find out what the electric field at this point is. Because it is 0 over here, therefore, if we move backwards, it will be WD times that slope quantity. So ES over here is Q Na times WD divided by epsilon S. Now, this is the electric field. So, and what else? What other information do we have? Um and we also know that. Yeah, so from this diagram, are you still here, Kumar?
Yes, sir.
So can you tell me how to find the potential difference?
Mm,
Like, do you know the formula for potential difference, like psi in terms of the electric field? Yeah, there's a little bit of like,
Right now, don't remember.
okay, don't remember. That's all right. I mean, it would have been nice if someone remembered. That's fine. That's fine. That's no issue. So the relation is essentially, see, I wrote, okay, I forgot to write that. Yeah, I wrote this, right? Gradient of psi is D, the displacement field, which is analogous to the electric field. So we can also write psi is equal to, therefore, integral EDX, or rather, EDR. Okay. So if we integrate the electric field along a certain direction, we will get the potential difference along that direction. Now I know the electric field is varying like this from here to here. So to get the potential difference, what I need to do is I need to find the area under this curve. So that is essentially this formula here. Psi s is half epsilon s times WD. Epsilon s is essentially this ES, this electric field that you see here, and WD is this. So it is just the area under the triangle. Is that clear?
Yes, sir.
So this is the area under the triangle. Uh, is everything all right? Okay, Chanshu is back. Good. Um, so from that, we can essentially do certain calculations to find out the approximate charge stored in the depletion region and the depletion region thickness. So we know epsilon s is also written in terms of WD. So substituting that in here, we will get this formula. Can you see that? So let me quickly move to the whiteboard so that way I can tell what is happening. So first we are looking at uh, depletion region width. Or rather, let us address everything over here. You can see the whiteboard, right?
Yes, sir.
Okay, good. So, yeah, let me just call it some important results regarding MOSFETs. So, when I say these are important, you know why they are important. I hope you know. So, this is for MOS electrostatics. So, the first thing we have is this. We essentially have an ES, and so there is a vectorial quantity, and over here, so this is the y-axis in the device. So like, since I've made all these conventions before, so yeah, let me just write it here. So we have how do I write this? Yeah, so I will just say x-axis is along the channel, and the y-axis is along the gate oxide body interface. Is this clear? Oh, yeah, change color. So this is the depletion width, and we know that ES is equal to minus Q, not minus, sorry, plus Na times WD divided by epsilon S. Therefore, and additionally, we also know that psi S comes from the area under this graph. So this is the E vector, that is the vertical axis of this thing. So that is half ES into WD. That is equal to half Q Na by epsilon S. Na times WD squared. So by back substituting, we can essentially get WD is equal to square root of 2 psi S into epsilon S divided by Q Na. Why am I writing small a's? Small a will make it sodium. Yeah, Na. All right. So this is the depletion layer thickness. So yeah, coming back here. So as you can see, that is the formula we have here. Is that clear? Hello.
Yes, sir.
Yeah, good. So how do we find the depletion layer charge? That is QD.
Means from this formula, na, sir?
Which formula?
Like QD equal to minus under root 2 QNA ES
Yeah,
psi
yeah.
S.
So how do we arrive at this formula is what I'm asking.
Okay.
See, I told you how to derive the depletion layer capacitance. So how do we arrive at uh, the charge depletion charge formula? So essentially, how we do that is we use the Poisson equation again. The second derivative of this quantity is equal to the charge, right?
Sir. Yes, sir.
So the second derivative of psi is minus QD upon epsilon S. So you write that, and this quantity is already like, so I know psi S over here. So to take the second derivative, what I'm supposed to do is essentially I should do d square by dy square. So you can do that by essentially assuming, so when the electric field becomes zero, you can say that the potential also goes to zero. So that should give you a slope of the potential. Take the slope of that slope, essentially the variation of that slope, and that should give you this quantity here. So that will approximately, like, that is the point. Like, you cannot exactly measure the second derivative from this equation and this graph only. But what you can do is make certain approximations on the variation of the potential, just like we made some approximations regarding the variation of the electric field, and then you will arrive at this equation. So these three equations are important. Uh, under the triangle. Yes. So now moving on. Yes. So when the time comes, remember these parameters. So psi b is essentially the intrinsic potential difference between the Fermi level and the conduction band. Is that like are you guys aware of this? Like you must have studied something about uh, charge carrier inversion in MOS devices. Are you guys familiar with that? Yes or no? I mean, you guys can say no. I mean, that's not a big deal.
Hello?
Yeah.
Maybe not covered that video, sir.
No, I mean, you've definitely not seen that video. What I'm asking is from your previous courses on MOS devices and so on, you must be familiar with the band diagram of the MOS capacitor, right?
Yes, sir.
So you know when inversion occurs. Like essentially, the energy difference, the potential difference between the conduction band and the Fermi level, like whatever difference that is, the Fermi level, the conduction band should bend below the Fermi level by that same difference. Do you remember this concept?
Think
Okay,
forget, sir.
okay, fine. So in case you have not, you don't remember it, go back and pick up any basic textbook on MOS devices that should explain that phenomena. So that is essentially where we get this relation that for inversion, psi s should be 2 times psi b, and psi b is given by this expression. And here, as you can see, we are using Ni. That is why I asked you what Ni square was initially. Like you're required to kind of remember these things.
Yes, sir.
Under inversion conditions, WD will be WD at 2 psi b because psi s has to be 2 psi b. So in this formula, in the previous formula that we derived, instead of psi s, we will use 2 psi b. Okay. So that is that part. And what else? Uh, so this equation essentially comes from Maxwell-Boltzmann statistics. So this is from Maxwell-Boltzmann statistics. Like this is n naught is equal to n is equal to some n naught times e to the power delta e by kbt. So this comes from that. And what else? What are the other more important things here? Uh, yeah, remember some of these relations. They may not be directly useful in your assignments, but again, in the lecture, sir will explain what these things are. Again, if you remember whatever I've told you here, you should be able to figure out what is happening here. So that is there. And yeah, so this is the basic notion of how the electrostatics calculations are done. This will be further continued in the next set of slides. So moving on. So yeah, all the results that we have previously uh, like studied are summarized here. Over here, the thing that you have to focus on is this relation over here, the inversion thickness that is given by kbt by q by E average. So this essentially comes from the fact that at high temperatures, what is the unit of kBt? Like what dimensions does kBt have? Okay, so this has the units of energy. So what will energy by charge give me? Come on, this you guys should be able to tell. Am I audible at least? Or do we have some signal difficulties? No, there doesn't seem to be any signal difficulties. So, yeah, can you guys tell me what dividing energy by charge will give us? Yes, yeah, potential. Thank you. So I suppose you have some signal issues, and that's fine. So yeah, where were we? Yes. So dividing potential by the average electric field will give us the thickness, the length. So the inversion layer thickness can also be calculated in terms of the average electric field and the the temperature of the device. So this is also a very important relation. So here we are essentially considering the average properties of the device, like in the thermodynamic limit. So this gives us the rough dependence of the charge accumulation in the mass device along the y-axis as a function of potential. So we have two regions. So we have the accumulation region, which at which case what will essentially happen is we will have, so as you can see here, this is log of mod of qs. So this is not the actual, this does not account for the sign of the charge carrier. This only talks about the number of the charge carriers. So for negative psi what will essentially happen is the majority charge carriers will be accumulated. So this blue line is for the accumulation of holes. So over here, this is essentially hole accumulation. Whereas this red line here talks about the electronic charge. Like this is essentially electrons gathering in the depletion region. So this is what is happening when we are looking at the inversion. So for how the variation will essentially happen is initially there will be a small increase after a certain point, and then for a very long time the variation of the accumulated charge, or rather the log of the charge, will be approximately square root of psi s. That means in this region what we will have is, so in this region we will have qs is equal to, or rather proportional to, e to the power exponential of some constant times square root of psi s. So that is what this graph means. So because this is the log here, okay. So if this has a square root dependence, that means it is e to the power that. And over here, the graph will slowly become linear, which implies there is a proper exponential dependence after strong inversion is achieved. So this region is the weak inversion region. Oh, sorry. And really, yeah, so this region is the weak inversion region, and this region is the strong inversion region. So, and all of these are determined by the value of the surface potential. That is essentially the potential at this point, like this region, the semiconductor insulator interface at this region. Okay, so that is that. And of course, based on these things, we can define device capacitances. So the most straightforward capacitance that we can define is the oxide capacitance. That is the capacitance due to the presence of the insulator layer. So the oxide capacitance is given by this quantity essentially. It is given by Qs by delta V oxide. So the formula is written in the opposite fashion here. And because of that, because of a capacitor being attached here, that will cause an additional potential drop. So when we apply a gate voltage on the gate electrode, the oxide layer, there will be a potential drop across the oxide layer, and then the surface potential will show up after getting deducted by the oxide layer. So essentially, Vg dash is the actual, like the effective gate voltage, like the fraction of the gate, like the amount of the gate voltage that is actually felt in the channel through the oxide layer is given by Vg dash. So this is the effective Vg, and that is given by this, like the difference is given by this quantity VFB. So that depends on the essentially the differences in the Fermi level of the metal and the semiconductor and the oxide capacitance. So it is phi ms by q and qf divided by Cox. So this is the delta V, like this is essentially the delta Vg that happens across the metal and the oxide layer when going to the semiconductor part. Therefore, because of this, what will happen is we can also see the dependence of the surface potential psi s with respect to the applied voltage VGS. Like the VGS is applied at the electrode of the device. So that follows this kind of a profile. So again, in this region, Qs is proportional to the square root of the potential, and over here we have Qs is gains an exponential dependence. So again, this region is the weak inversion region, and this is the strong inversion region. So what you can also see is that once inversion is achieved, the surface potential here actually does not vary much. Like the surface potential only increases up to a certain point, and after that it remains roughly constant. This is the line where psi s is equal to Vg prime, but that never happens in a device. Okay, is that clear? Yeah, I hope it is clear to you. Like, I mean, I hope you guys can understand that. Like, again, these are things that you just have to know what it is. During the lectures, it will be explained in greater detail. Since we have to effectively cover the content of all 5 lectures and also do some problem discussions, I'm kind of moving a bit fast. So kindly bear with that. And based on all of these quantities, we can also define what the threshold voltage of the MOSFET is. So the threshold voltage is essentially the voltage at which inversion is achieved. Now we know in order to achieve the inversion, psi s has to be 2 times psi b. But to achieve 2 times psi b over here, we have to apply Vg plus whatever other, like the delta Vg should be applied here. So essentially VFB is also needed. So the threshold voltage will be 2 times psi b plus VFB. So it will be a sum of all these quantities and plus the, what to say, like the oxide capacitance charge. So the threshold voltage will have this kind of a relation. This part is also important. And finally, we can get the net gate capacitance. The gate capacitance will be a combination of 2 capacitances, like these are 2 capacitances in series. One is due to the presence of the insulator, the oxide, and the second is due to the semiconductor itself. The semiconductor also acts as a dielectric. So Because of that, the gate capacitance will be written as like for two capacitors in series, this is the net capacitance. In the inversion region, the gate capacitance is approximately equal to Cox. In the accumulation region also, this is true. But in the intermediate region, in the weak inversion region, we need to take into account both the capacitances. In fact, that is the reason why the charge accumulation pattern shows this kind of a growth. So, yeah. So from this, we get a very important parameter. This is quite important. So now there are two capacitances. So when we are charging the device, and what you have to remember is like, so this is essentially the arrangement of the device. So CS, this is in the body. Oops. So this is in the body. That implies this is a variable capacitance and this point is the interface. This is the oxide semiconductor interface. So this is the, let me just, because there is not much space, let me just write this as the OS interface. Okay. So what essentially happens is in the depletion regime, essentially where what we call the weak inversion, like where there is charge depletion occurring over here, the effective capacitance is actually closer to the combination of these two quantities, like the device capacitance and the oxide capacitance. So because of that, the psi will depend on the capacitance values Cox and Ct. So from this we can derive a quantity that is called the body coefficient. So m is the body coefficient which is given by 1 plus Cb by Cox. So Vg, like psi can be written as Vg by m effectively. So everything that we have discussed so far, like the potential energy difference and the gate capacitance and the other charge accumulation effects, can all be summarized into one effective parameter, that is the body coefficient m. All right. Is there any difficulty? Like you guys can tell me if there are any difficulties. Like it seems like you guys are not as interactive as before.
Hello,
Yeah.
sir.
Yeah.
Sir, any other theory like to go for that small m value? Means
Any other theory? What do
any
you mean?
other definition like other concept?
Other concept is not. I mean, it's a fairly straightforward thing to study in terms of the capacitance itself. See, what is happening here is where were we? Yes. So see, what is happening here is there are two capacitances.
Cox
Vg
and
is,
CD.
huh?
Like Cox CD.
Yes. So there are two capacitors here. A voltage is applied here. This terminal is grounded. I need to find out what the voltage in the midpoint is. So how do we find that? We do the voltage divider equation, correct?
Yes, sir.
So that is essentially what is being done here. That is all. Like there is no deep theory here.
Okay, sir.
Okay, so this is the voltage at this point. So psi s based on this diagram, like this leads to this. Okay, and from this we derive what is known as the body coefficient. The body coefficient is essentially just the ratio between the depletion capacitance and the oxide capacitance.
Understand, sir.
Okay,
Means in there. In that side, just you have taken M equal to 1 plus CD upon Cox and
Exactly.
you
That's all.
replaced with that. Yeah.
That is all. Okay. So there is a question based on the body coefficient in the assignment. So that is why I'm saying this is important.
Yes, sir.
Right. So that is the thing. Like whenever you're looking at the body coefficient, remember that the body coefficient appears in the connection between the surface potential psi s and the gate voltage Vg. Okay. So that brings us to the end of the second lecture content. Now this is further summarizations. So yeah, so here the body coefficient is discussed in greater detail. So first and foremost, this capacitance, the oxide capacitance, this is just a parallel plate capacitor. So we know that the capacitance of a parallel plate capacitor is given by C is equal to O. Yeah. Can you tell me what this formula is? It is usually given by epsilon A by D. Parallel plate capacitor. So this is your old electricity and magnetism from high school. Yeah. Yes. Capacitor. So this is that formula, but here Cox is, this is per unit area, because we do not know what the cross section area of the gate is. Therefore, we always define capacitance per unit area. Okay, so this is the value of the oxide capacitance. So the oxide capacitance is a constant, and this part is the depletion capacitance. So the ideal value for, so remember that from the previous slides, in the strong inversion region, the gate capacitance is equal to the oxide capacitance. That implies the depletion capacitance goes to zero. Oh wait, does the
Yes, sir.
depletion capacitance go to zero? No, the depletion capacitance goes to infinity. I'm sorry. I'm sorry. So this is one by CB, right? So like for these two to be equal, yeah, CD should go to infinity. I'm sorry, it shouldn't go to zero. Yeah. So oh, let me open this. Yeah. So since we are writing important results, yes, let me go ahead and write the second thing. Uh, I hope you can guess why I'm writing these relations separately over here. Cox plus CD times Vg, which is equal to Vg by M, where M is equal to 1 plus CD by Cox. Yeah. Yes. So now, ideally speaking, I will want psi s to be as close to Vg as possible. Correct? I don't want to lose too much voltage in the oxide layer. Right? Because that implies energy is unnecessarily getting dissipated outside of my device. I want all the impact of Vg to go directly into the channel. Therefore, I want M to be as close to 1 as possible. So how do we achieve that? We can achieve that by increasing the value of Cox. Like this combined quantity should go to 0. Now I cannot make CD go to 0. So what I will have to do is I have to increase the oxide capacitance as much as possible. How can I do that? We know per unit area the oxide capacitance is epsilon ox by thickness of the oxide layer. So decreasing the oxide layer thickness will increase the oxide capacitance. Is that clear?
Yes, sir. And also increasing the dielectric value, it also
Of
increases the
course.
capacitance.
Exactly. But tell me this. Now you've raised a very good question. Like, thank you for raising this.
Yes, sir.
Can we always do that?
No, sir. It's also depend on the like situation.
No, no. Like I'm asking, how easy is it to modify the dielectric constant of the insulator? Like I thank you sincerely for raising this point. Like this is a
Yes,
very,
sir.
very good point that you've raised. So
Sir, because suppose in a
uh,
chip there are lot of ICs are there. We
uh-huh.
cannot replace all the dielectrics with different material all the time. But
Okay.
we can modify the thickness when we are
All
fabricating.
right, you're correct about that. But why can't I use a higher dielectric insulator while fabricating it itself?
And also,
So essentially, the idea is this: like there is a reason why MOSFETs are called MOSFETs.
yes, sir.
It is because the insulator layer is obtained by oxidizing the silicon itself. If you remember your, the etching process and your photolithography and all of that,
Yes,
what we
sir.
essentially do is the oxide layer is obtained by just directly oxidizing the silicon that is on the substrate.
Understand. That's why silicon dioxide preferably we
Yes.
use. Right, right.
So, and the advantage is that the lattice matching between SiO2 and Si is very good. So the
Yes,
oxide layer will actually stick. So I cannot just randomly pick some insulator and stick it on silicon, or take some other insulator and stick it on some other material. It is important for their lattice parameters to match. Only then and then will these junctions form, and after that the device will behave. Like I cannot just throw sand on a metallic plate and say this is a MOSFET.
yes, sir.
Like they need to bond at a molecular, like an atomic level. So any random insulator cannot be brought into the device at will. Like there are several fabrication challenges. But if we can somehow reduce the oxide thickness, then of course we can increase the oxide capacitance and thereby bring the body coefficient closer to 1. Okay.
Yes, sir.
All right. Good. I hope you're
Sir,
also. Yeah.
one question
Yes.
I in my mind, yes. And because of the thickness, one more capacitance is like side wall capacitance also comes into picture.
Yes, that comes in, but right now we are assuming that is the thing. That is why we are talking about per unit area here.
Yes, sir.
Okay, like we are not looking at the finite size effects of the gate. Yeah, in that
Understand.
case, we will have sidewall capacitances, we'll have fringe capacitances, and all those things. But we are not discussing them here. Right now, we are just looking at the size factors. Like, the essentially in the even in the idealized situation we are considering, we are looking at what the challenges are.
Okay, sir.
Okay.
Yeah.
So, so another way is essentially to reduce the depletion capacitance to make it very small. So for that, an approach is to use lightly doped semiconductors. So in that case, CD will become very small because CD is proportional to square root of the dopant atoms. So if I can reduce this, we can, kind of achieve what to say, like a smaller value of the body coefficient. Like body coefficient can approach 1. The third approach is of course by use of high K dielectrics, as you mentioned. So some of them are hafnium oxide, hafnium dioxide, hafnium silicate, zirconium dioxide, and zirconium silicate. So, but again, depositing these materials, like most of these, I think, can be done using some kind of molecular beam epitaxy. But
Yes.
again, those methods are all like, it's
Complex.
serious stuff. Like you cannot do it very easily.
Mm.
Okay, so that is why manipulating the geometry of the device is easier. Plus, hafnium and zirconium, these are all very rare earth elements. Like I cannot create those devices and say these will be mass manufactured, and such transistors will be present in every processor of every smartphone or laptop or PC. We may not
Understood.
have that much hafnium or zirconium, or production cost or the actual device costs might skyrocket. Which is why geometry becomes very important. Which is why this course does not focus on high K dielectrics or the doping profiles and these things. We focus more on the geometry, because that, even with available silicon, which is somewhat cheap for now, who knows, maybe in the future even that will become expensive. But right now it is still readily available. So using just that, can we make devices with better and better performance? So that is essentially the thesis of our discussion in this course. An additional thing that you can notice is, of course, all of these things will change. Like, these are for electrostatics only. In the presence of time dependent signals, like when there is a frequency applied to the external signal, these capacitance values will be replaced by their respective impedances. So, in the low frequency and the high frequency domain, the action of these capacitances will be different. So that is just being pointed out here. It will not, most likely not be used in any of the questions. So during the lecture, you can pay attention to that. So that is that. And now finally, so that is the thing. So essentially, when we discuss the MOSFET electrostatics, that is along the y direction. After solving all the equations and everything, effectively we can talk about two capacitance. Like, this is the understanding that we have, that the effective model to a good extent can be studied as two capacitances in series and the surface potential here. The charge present in the channel depends entirely on psi s, and psi s is connected to the applied potential Vg via the body coefficient. So this is the final summary of the MOSFET electrostatics discussion. Okay. So another thing that we can derive is, of course, our old discussions, the idea of drain-induced barrier lowering, and another concept that we call as the threshold voltage roll-off. So we will see that now. So DIBL, I hope you guys remember, like essentially the barrier height is lowered by increasing the drain voltage.
Yes, sir.
Okay. So in the ideal case, of course, we do not want that to happen, but in a realistic case, that will always happen. So now we are not just doing electrostatics in one dimension. Now we have to consider electrostatics in two dimensions, in the x direction and the y direction, in order to study things like DIPL. So how do we start by doing 2D electrostatics? Same method as before. We start with the same Maxwell's equation, but now instead of just taking the derivative with respect to one length coordinate, we will take it with respect to both the length coordinates. But luckily, in our previous analysis, we have derived all these results for the y variance. So whenever the y-axis terms show up, like the d square psi by dy square and all of these things show up, we'll just substitute the results that we previously derived. So that is a very good approximation. Okay. So essentially, this is what we do. We write d square y by dou square psi by dou y square as this, and we also know that since VDS is positive, like VD is at a higher voltage than VS, which implies the electric field will point in which direction? Will it be from S to D or D to S? As a hint, electric field is minus gradient of, is equal to minus gradient of V. This is the higher voltage, this is the lower voltage. So essentially the gradient is delta V by L. So delta V by L in this case will be positive, but we will be taking minus of that. So the electric field will be in this direction due to the drain source voltage. Is that
Okay,
clear?
sir.
So because of that, when we take this quantity to the other side of the equation, d square psi by dx square will be positive from the source to the drain. Like the second derivative will become positive. So what is essentially happening? Like remember what we discussed in this slide over here. We said d square psi by dx squared is equal to minus q epsilon s by times Na, right? For a p-type semiconductor. This is what we wrote for 1D electrostatics. Now what is happening is, in addition to that, we now have the other term. We have this term that is newly appearing. Okay, but 1D or 2D, the charge in the material does not change. Okay, and there are no free charge in the oxide. So 2D electrostatics in the oxide layer will just give me this equation because there are no free charges in an insulator. Okay. Now this part, like, so this is the, like, oh, wait, let me just erase this. Oh, yeah. Yeah, so this equation is the effective 1D Poisson equation. Like this still looks like the 1D equation. What I'm doing is I'm taking the x dependence to the right hand side, and yeah, I know Poisson should be P should be capital, but I'm sorry, I started writing that. So this is the effective 1D equation. So now what we will essentially see here is that this quantity can be absorbed into Na. What I can do is I can multiply and divide by epsilon s by q and absorb it into this. So I can write dou square psi s by dou y squared is equal to q by epsilon s into Na minus uh, epsilon s by q dou square psi s by dou x square. Is this clear?
Yes, sir.
So now I know this quantity is positive. These two are positive constants. So essentially what is happening in like this, the charge in this in this bracket is coming down. It is getting reduced. Like this is written as Na effective. So that is what you see here, Na effective. Is this manipulation clear?
Sir, how it is reducing there? So the
Because
NF.
see, d square psi s by dou square psi x by dou x square is positive.
Okay.
Like how is it positive? Because when I go from source to drain, how will I take the derivative? I will take the latter point divided by the former point, right? Vd is held at the higher voltage. So
Yes,
I
sir.
will take Vd minus Vs divided by delta L. So this derivative will always be positive. It will be greater than or equal to 0.
Okay, sir.
Like from source to drain. This is important. From source to drain, d square psi by dx square is positive. And because of that, as we are moving closer and closer to the drain, the effective charge available keeps coming down, keeps reducing. And that is why the potential profile also keeps going down. Is that clear?
Yes, sir.
So that is how we explain DIBL using electrostatics.
Okay.
Now see, higher
This the
DIBL, huh?
with the role of capacitance, how it is reducing right now. Yes.
Yes, exactly. So right now we have written it in terms of potential. Now we will see what happens in terms of capacitance.
Yes, sir.
Okay, so Na effective will always be less than Na, and higher VDS, smaller NAF. Okay, Na effective. So now you can ask, okay, so how can we study this in terms of the capacitance? Because you see, this expression, you remember the threshold voltage, right? Vt is equal to VFB plus this quantity due to the oxide capacitance. There is an Na over here. But if I have to include the 2D effects, Na should be replaced by Na effective.
Effective.
And what is happening to Na effective? Na effective is coming down.
Reducing.
Since Na
So
effective is coming down, the threshold voltage will also be brought down.
understand, sir.
Okay, so that phenomena is known as the threshold voltage roll off. Okay.
So that day, sir, I asked you that how threshold voltage is changing. So this is the
Yes.
answer, na, for
Yeah,
that.
this is the answer to that. Yes, you're correct.
Right, sir.
Okay. So this, like, if you can understand these notions, you can understand. I mean, you have a rough idea of what is happening to 1D and 2D electrostatics in a MOSFET. And this theory is broadly true for even nanoscale devices. Okay. So, uh, what was I about to say now? My God, I just lost my thought. Yes, we will not be looking at explicit numerical solutions of these Poisson equation and all of that. Like if you really want to do device simulations, you need to numerically solve these equations. 1D and 2D electrostatics. Like you'll see some of that later on when I show the papers. But right now in this course, we are not going to do that, but we will give you a qualitative understanding, like especially through these terms, as to why these phenomena are happening. Okay. So there is that. So lecture 4. Yes. So again, this is a summarization of everything that happened in 2D devices. Yes. Now we are coming to the practical effects. So now we are talking about screening and quantum confinement and from so everything that we have been discussing so far. So let me just we still have around 45 minutes left. That should be enough time. So uh, yeah. So before we continue, the reason why we have been learning about the physics of nanoscale devices is essentially to see what kind of manipulations and what kind of techniques we can use in short channel devices to enhance their characteristics. By enhancing their characteristics, what I mean is Vt should be roughly a constant. It should not depend too much on the drain source voltage. There shouldn't be any DIBL. There should not be any kind of subthreshold swing happening. So, these are the behaviors, ideal behaviors of a MOSFET that I would like to see. The threshold voltage should be high enough and it should not, be easily variable on other quantities. It should have good thermal sensitivity. And, these are the things that we like in a ideal MOSFET. So our aim, the ultimate aim of our course is to study the effect of various parameters on nanoscale devices and hopefully identify what are all the good traits that we can obtain by doing certain modifications on the device. So ultimately, it is not only important to understand the Landauer transport model, it is also important to understand under what kind of geometry will Landauer transport be enhanced. Under what kind of geometry will I have better electron carrier mobility? Under what kind of situation and structure, what kind of channels can we expect to have a good, what to say, like protection for the barrier characteristics from the drain source voltage. So this is the ultimate aim of our course. And with these set of slides, we begin that. I know this is kind of like coming at the last 2 weeks of the course, but fortunately or unfortunately, that is how the course is structured. there is a greater emphasis on the basics so that the latter part you guys can do even on your own time based on your own reading, because there is not just one unique solution for improving the performance of a MOSFET. There are several techniques, some of which I shall briefly introduce in today's discussion. But that is the thing, that is not the limit. Uh, Day upon day, more what to say, like geometries, more device configurations are being studied and developed, and some of you might go on to work in that field as well. So, given that, it is imperative that you guys know the basics so that you can use these as tools to tackle those higher level problems, rather than just focus on a handful of high level problems and talk about specific techniques. Our aim is to ensure that more of the basics are emphasized and we give you a flavor of what is happening at the higher level implementation. So
Yes, sir.
yes, the first phenomena that we are looking at is called screening. So essentially, what is the notion of screening? The notion of screening is just this. If in a material, any material, this is actually true at very large levels. Like screening is not only observed in semiconductors, it is observed in like a large array of natural phenomena. So typically when we introduce an external charge or create a kind of a charge perturbation, what will happen is the charges that are present in the material will quickly reorient themselves to prevent the uh, effect of the charge perturbation. Like essentially, if I create a perturbation, the material will respond to oppose that perturbation. So, one very common example that you can think of is if we have a metal, like, so you must be familiar with electromagnetic shielding, right? Like, are you guys familiar with the concept?
Shielding of device, sir.
Yes, electromagnetic shielding of devices. Like, how do we do that? We essentially put a metal
To
cage on it.
avoid EMI, electromagnetic interference.
Yes. So, how do we do that? We just put a metallic box on it.
Yes, sir.
So, what does the metallic box do? When an external electromagnetic perturbation, electric field comes, it will just reorient its charge configuration such that it cancels out the external electric field.
Okay, okay. It means it will reflect down outside. Like,
Exactly. So that phenomena, why does that happen? Because the metal has a lot of free electrons. So the electrons can move and reorient themselves in whatever configuration to reflect that electric field.
yes, sir.
So that phenomena is essentially what is at the heart of, like, screening is the reason why that happens. So that is why, like, if you again study some electrodynamics, you will see that there is these notions of a penetration depth for electric fields and so on and so forth through a metal. So a similar quantity for the screening phenomena is what is known as the Debye length. So the Debye length is given by this formula. It is epsilon s kBt by q square n naught, where n naught is the intrinsic charge carrier like the charge carrier concentration in the material. So if it is doped, you are supposed to use that. If it is an intrinsic semiconductor, you are supposed to use the intrinsic charge carrier concentration. Okay.
Sir,
Yeah.
sir, any suggestion for doping in nanoscale device? Like suppose in the bulk we are doping, then fabrication is somewhat easy, but in the nanoscale,
Yeah.
is the doping is difficult or like to control the exact doping concentration in that region?
Good point. So typically, as you will see pretty soon, is it in the next slide?
Just asking, sir, basic idea behind
Yeah,
it.
yeah, yeah. I'll show you. I mean, why would I hesitate? So see, like for nanoscale devices, this is a very nice structure.
Yes, sir.
Okay. So what is this device? These are called SOI or ETSOI MOSFETs.
Silicon non-insulator device.
Yes. So what do we mean when we say silicon? It is undoped.
Okay, sir.
See, because as you very correctly mentioned, in a small size device, maintaining doping concentrations is very difficult.
Yes, sir.
So what do? We don't dope it.
Okay,
We
okay.
just ignore doping.
Okay, sir.
So yes, as we are moving further and further and like farther and farther and farther, you will see that the concept of bipolar junctions or multipolar junctions, where I essentially have a PN junction and all of those things, that itself will change. Now what we will have are strain junctions. Like
Okay.
essentially there will be a lattice strain on one layer and there will be no lattice strain on another layer. So I will show that when I'm looking at
You,
a like
you point out the
review
you
article.
point, yes, sir. You point out the great idea that is strain word. Actually, na,
Yes.
why I am telling about doping is because suppose in graphene, na, generally we do band gap engineering. That's
Yes.
why we are doping the like channel region. So
Yes.
mostly the band gap is open also because doping and also because of the that you told lattice strain.
Yes.
Right, sir.
Yes. Okay. So yeah. Uh, wait. Okay. Yeah, we are here. Yes. So this thing is being written. Right. Yes. So the next important thing is the screening length. Uh, where yes. So let me just open a new slide. So yes, more results. So first we have the Dubai length LD. So this is square root of KBT epsilon s divided by q squared n naught. I hope I've written this correctly. Uh, let me check. Yeah, that's correct. So this is, oh, uh, yes, so this is the characteristic length of screening. Okay, this is the characteristic length of screening. Now, so what does that mean? Let us see. So one of the parameters that we discussed, like that we saw, is DIPL. That is drain induced barrier lowering. When does that happen? That essentially happens when the applied drain voltage goes and attacks the gate voltage. Right? Hello.
Yes, sir.
Yeah.
I'm here.
So you can hear me, right? Yeah, I suppose you can hear me. So the idea is this is the drain
Yes, sir.
terminal. So DIPL occurs when the electric field from the gate goes and impedes with the, like essentially the charge accumulation here will affect the potential applied here. Now, how do I prevent that? If there were perhaps enough charge carriers in the channel to screen that applied potential, then maybe the electric field will not reach the gate, and because of that, DIPL will be reduced. So, for reduction of DIPL, this is typically how we do this. Like essentially, lambda, which is the gate length, which is also the channel length, should be greater than the Debye length, essentially. So, because at the Debye length, screening starts happening. Greater than that, screening effects are very strong. Less than that, screening effect is not very strong. So, the general threshold is L should be approximately to the order of 3 times lambda. In that case, DIBL is low. In
So that
general,
is 3
yes,
lambda or 3 after 3 what's it is written?
that is lambda. That is capital uppercase lambda.
Okay, sir.
So like, is it lambda? Yeah, that is lambda. Yes, that is lambda. So essentially, what we are saying is the more we are surrounding the channel with the gate electrode, the more effective the screening will be.
Hmm.
Okay, so in our standard configurations, what essentially happens is only one side the gate is present. So on one side, the gate will handle the screening, but on the other side, the electric field directly affects the body. Since it affects the body, what will happen? It will push the charges that are coming into the inversion region. Is that clear?
Yes, sir.
So since there is an electric field here, any charge that wishes to enter the depletion region will have a difficulty. But if we put a gate on that side too, then what will happen? This electric field will also be screened off by the gate. So that is essentially why we have multi-gate devices.
That's why sir FinFET having lot of
Yes,
advantage.
yes. So in general, lambda bulk is the largest. Double gate SOI is smaller than that. Nanowire transistors have even better performance. But of course, fabricating a nanowire is difficult. So, three times this quantity is the minimum channel length you can have for low DIBL. So, since this is small, nanowire transistors can have the smallest channel lengths, followed by double gate silicon on insulator transistors, and bulk transistors, therefore, require to have very long channels. Okay, so that is the effect of screening. So now we come back to yeah. If you can remember way back when we did some calculations for the de Broglie wavelength. So over here you'll see that the de Broglie wavelength approximately for at 300 Kelvin for an electron is around 6 nanometers due to just the thermal energy. So the thermal energy is given by 3 kBT by 2. So this comes from the law of equipartition. So from that we derive the momentum, and from that we get the de Broglie wavelength. So the thermal wavelength is around 6 nanometers. So in principle, if my device channel length is less than 6 nanometers, then quantum effects will become very strong.
Okay.
Okay. And what is the limit in which we are working these days? We are working in around 5 to 10 nanometers. So quantum effects are going to become very, very strong. So now, what happens when we have quantum effects? So what happens is essentially this. Since quantum effects become pronounced, what we will see is we will see, like, you guys might remember the notion of subbands and all of that, correct? From our previous lectures.
Sub bands, na? Due to
Yes,
quantum confinement.
yes,
Yes.
yes. So now we should not only look at the band structure of a device, we should also look at the subband structure of the device. Okay.
Yes, sir.
Now, in those cases, how do we, like, create the potential profiles and see? Here we just had simple bands. Since we had simple bands, we were able to find out threshold voltages, we were able to find out charge accumulation and all of those things. That was all very easily analyzed. Now, how will you analyze that for devices where, there are subbands, there are, other structure dependent parameters? So how would you create a transistor for that situation? So essentially what we do is, first we understand that when we do confinement like this in a device at the like below 20 nanometer regime, first thing we are supposed to remember is the electron will behave as a 2D electron gas or a 2D hole gas. Okay, so this part we have discussed before. Like in the xz direction, the energy will be continuous. In the y direction, the energy will be discrete. This part, like I think in week 5 or week 6, we discussed this. The video slides, everything are up. You can go back and revise these. So because of that, we will essentially have like the formation of subbands, and because of that, calculation of quantities such as electron mobility and things like that will change. These things will be covered in greater detail in I think in the next slide itself, if I'm right. So yeah, we'll see about that. Oh yeah, yes. So we'll leave this here and continue from the next slide. Yes. So again, summary of everything that was there before. And yeah, so this, as you guessed, is the FitFET structure. What you have to remember is at 6 nanometer, all kinds of quantum effects begin. So quantum, wait, like this is for a device operating at room temperature. So one way of, so as you can see, if you want to increase this lambda, one way is to operate the device at low temperatures. If I can reduce the temperature, lambda b will increase. Is that clear?
Yes, sir.
So that is also one thing people have proposed, but that is not always going to be possible. Like if you want such a transistor to be present in a smartphone or some device that we are carrying mobile, then we cannot expect it to work at low temperatures at all times. So that is why changing temperature is not discussed as frequently. So like at 6 nanometers, oh, still a very soon. Yeah, at 6 nanometers, quantum confinement is significant. Okay, confinement. So let me write this result also. So this is the thermal de Broglie length. So this is h divided by square root of I think it is 3m kbt. Yes, 3m star e kbt, and assuming m star is equal to me, this is of the order of 6 nanometer at 300 Kelvin. Okay. So yeah. So yes. Now, before we talk more about quantum confinement, let us quickly come back to, like we previously discussed, that screening will be better for double gate MOSFETs. So one verified, or rather, like now it has been tested well enough. Configuration is the double gate silicon on insulator MOSFET. So over here, what essentially happens is we have intrinsic silicon and a thin layer of oxide and two gate electrodes. So the source drain current is applied directly across the silicon layer. There are no separate source and drain regions with any kind of doping gradients. Okay, so this is your silicon on insulator MOSFET. So the potential profile and the charge carrier concentration in here is varied by changing the gate voltage. Since this device is symmetric, what we will notice is that accumulation and depletion follow the same trend. Whereas previously that was not the case. Why? Because the material was a p-type material. So hole accumulation happened very easily, but electron accumulation happened with a lot of challenges. But here that is not the case. It is symmetric. So these devices can potentially work equally with both the positive gate voltages and negative gate voltages. So there is that. And additionally, the net free charge in silicon, since it's an intrinsic material, is always zero. And because of that, what happens? Can you guess?
N effective will be less, like Na.
No, no. There is no Na. There is no acceptor. Think of the depletion capacitance. What will it be? Or rather, tell me what will the potential drop across the depletion capacitance be if the total charge is zero?
Hmm.
Q equal to CB. Correct? Now, if Q is equal to zero, then CB is also equal to zero.
Zero.
That implies there is no voltage drop across the depletion capacitance.
Hmm. Yes, sir.
So VG will be equal to psi S, like minus Tox.
Yes, sir.
Is that clear? So there is no more effect of depletion capacitance in these devices because there is no depletion region to speak of. We are in an intrinsic semiconductor. All right. So that is why you don't have that depletion curve over here. If you remember from these slides, if I'm right, yeah, you see this right. This region is not present at all when you come here. It just rises. So as you can see here, there is no like the where is the body coefficient? Where have they derived it? Oh yeah, they have yes. So Vg prime is yeah. So Vg prime is equal to psi s. There is no body coefficient here. Body coefficient is one because CD is zero. Okay. So the only potential drop as that occurs from the gate to the silicon is across the oxide capacitance. Okay. So Vg dash is equal to minus this quantity, and that is that. So because of that, Vg dash is equal to psi s. Okay.
Yes, sir.
So because of that, what will happen is for a double gate silicon on insulator device, the psi s will follow Vg dash. But previously we saw for a bulk MOSFET, it did not. It was always less than that, and eventually it, flattened at around 2 times psi b. But here it will follow it very closely, and when inversion, or rather when the critical amount of charge has been accumulated, it will reach this point and become a constant voltage. So this has a better like the gate has a better control over the surface voltage. Is that clear?
Yes, sir.
Like in fact, gate has complete control over the surface potential
It's an
in the
advantage.
subthreshold regime. Okay, so that is one of the key advantages of this device. So now we come back to quantum confinement. So there can be two forms of confinement. So essentially, there is quantum confinement even in a bulk MOSFET. So how does that happen? Can you tell me?
Quantum. Well,
So what is the like? Okay, do you remember? Not remember. Like yeah, see this depletion layer width. Okay, so now this is the first calculation that I'm asking you to do uh, for a surface potential of 1 volt. Okay, and do you know what the relative permittivity of this thing is? Silicon is. It's around 11 or something, right?
silicon
11.8 or something.
dioxide, sir.
No, just assume silicon for now.
Okay. Relative permittivity.
Yeah, what is
I think
relative?
4, sir.
4. What is it
Epsilon.
for silicon dioxide?
For silicon dioxide, it's 4, sir.
Okay, and for
Epsilon
silicon?
now. For silicon, don't know.
Okay, so for silicon dioxide, it is 4.
4, right, sir.
Okay. Now, okay, wait. Let me quickly stop sharing and get you the parameters. So that will be the first numerical calculation that we are doing for today. Uh, yeah, just 1 second. So Yeah, it's around 11. It's around 12 for silicon.
Okay, sir.
Okay, yeah, I was remembering it correctly. So, can you quickly calculate what the depletion layer thickness will be for psi s equal to 1, and assume Na is some 10 to the power 16 per centimeter cube? Can you substitute these and calculate?
No calculator right now.
Oh, no calculator. That's unfortunate. Okay, so quickly let us go to the whiteboard and write down the numbers. I will do the calculation.
Yes, sir.
Don't have to worry. I have a calculator. So uh, let us quickly try to calculate WD psi s is equal to like let me write it properly. So let me say like this is just to get an idea. Okay, psi s is equal to 1 volt.
Sir, please share.
Oh, okay, okay. I'm sorry. I'm sorry. I'm sorry. Yeah, but either ways, if you look at the video, nothing will be missed because my screen is being captured constantly. Um, what was I saying? Yes, share. Yeah, screen. Uh, yeah. So Chanshu seems he had a lot of signal issues. That's all right. Hope he catches the videos afterwards. Uh, yes. Is it visible?
Yes, sir.
Okay, and let me say Na is equal to some 10 to the power 16 per centimeter cube, and epsilon s is 12 times epsilon naught. Okay, approximately. So now, what is WD? So WD is square root of uh, yes, it is square root of yes. Yeah, it is square root of 2 epsilon s psi s divided by q times Na. So let me quickly substitute the values, or rather, let us just write that here. So that is 2 into 12 into epsilon naught into 1 divided by. So this is per centimeter cube. Since we are using SI units for everything, this has to be converted to meter cube. So if we convert it to meter cube, a factor of 10 to the power 6 will arise. So I'm going to write it as 10 to the power 22 into 1.6 into 10 to the power minus 19. That is the charge of an electron. So let us see what the answer comes out to be. Let me calculate it quickly. Yeah, you can also do some back of the envelope calculation and give me an approximate answer if you can. Uh, that I mean, I'd appreciate it. Yeah. Oh, wait. Yes. Yeah. So the answer comes out to be uh, around 3.7 into 10 to the power minus 7 meters. Okay.
Okay, sir.
Now, of course, now this is for like 1 volt. But typically, what is the range of voltages in like your like what is the range in which you will see the voltages vary in your devices in your MOSFETs?
Mostly the
Usually,
minus 2 to 2.
yeah, usually from minus two to two. But I'm asking like when we are looking at like switching and all of these things, like to what range do you expect these voltages to vary? Like that, usually the fraction of a volt, correct?
Yes, sir.
So essentially, now this, as you can see, even this is around what? It's around
Yeah.
300.
0.3 micrometer.
Yeah, it's around like 300 nanometers.
Yes, sir.
Okay,
The-
approximately.
Hmm.
So all the charges in a MOSFET are present within this depletion region when an inversion occurs, correct?
Yes, sir.
Right? Oh, wait. I should not have calculated this. I should have calculated T inverse. All right, I mean, that is fine. So, what you will find, okay, so this is the depletion layer thickness. What you will see is that the inversion layer thickness will be a fraction of this. So, it will be tens of nanometers. Yeah, that's why I was like, this is a bit too large. So, it will be tens of nanometers actually. So, what is T inverse? T inverse is KBT upon, KBT upon Q divided by epsilon average, or rather, not epsilon, electric field average. Oh, yeah, let us do this. Why the hell not? So now we have found out the depletion layer thickness, right?
Yes.
Yes.
Yes, sir.
Huh. So, and I told you psi s is 1 volt. So, can you tell me what the average electric field will be? It varies by 1 volt across 300 nanometers. So it is delta V, like epsilon average, or sorry, E average is 1 divided by 300 nanometers.
1 by 300.
Is that clear? Like it is delta V by delta X, right?
Hmm.
So it is this. Now substitute that into this quantity. Yeah. And that should give us the inversion layer thickness. So let me calculate that. So that is, okay, divided by, yes. So this is 1 by 300 nanometers. So when I divide that, 300 nanometers will go up. So I just have to multiply it by 300. Yes. Yeah. So the inversion layer thickness, yes, now we are talking. Yes, it comes to 7.75 nanometers for this. Okay. I urge you to do these calculations on your own.
Yes, sir.
Okay. Like this is because it's delta V by delta X. So Now, all the mobile charge carriers are confined within the inversion layer. Is that correct? I mean, am I correct in saying that? The inversion region is where I have all the electrons in my channel, right?
Yes, sir.
And so, what is the region in which those electrons are present? Around 8 nanometers. That is all. So, even in a bulk MOSFET, there is confinement. So, there is a potential well, and this thickness is around 8 nanometers. Or, sorry, not this thickness. There is a potential well like this due to the electric field, and the characteristic length of this is around 8 nanometers, at least based on the calculations that we did.
And channel length, sir? If
It is actually independent of the channel length. Like channel length doesn't matter, right? It just depends on the electric field applied across the y-axis.
yes,
For
sir.
bulk MOSFETs, the channel length is very long. That
Yes,
is
sir.
why these quantum effects are not very significant.
Hmm.
But as the length becomes shorter and shorter and shorter, these quantum effects become more and more prevalent. Okay, so there are two kinds of confinement. So this is the kind of confinement you see in a bulk MOSFET due to an external potential. And this is the kind of confinement you see in an ETSOI MOSFET. This is called geometric confinement. Okay. So in that, what essentially happens is the energy levels of the electrons are quantized. So you can no longer treat them as purely classical particles. And the analysis of all of this has been done before. How do we take care of the conduction? We take care of it by using Landauer model. We calculate the modes, we do all of those things. That by now you should remember. Okay.
Yes, sir.
So now finally we are, yeah. So the last part we shall be discussing, looking at today is this notion of the band structure of silicon with confinement. So now tell me this, whichever be the case, be it a 2D like a double gate silicon on insulator or a single gate device like this, in which how many directions is silicon getting confined? Like in how many directions is the movement of silicon getting constrained? Tell me in this case, can the electron move freely in the x direction? I mean, the electron can move in the x direction rather freely. There is nothing blocking it. It can move from this terminal to this terminal, correct? Hello. Oh, okay. I will have to disconnect and reconnect. Yeah. Uh, can you hear me now? Hello. Still seems to be an issue. Yeah. Am I audible, Kamal?
Yes, sir. Now you are audible.
Okay. So what was the last thing I said? Let me resume from there.
Mm, last thing you told about this is the last content we have to cover.
Okay, fine. So I've been cut off for like the better part of 2-3 minutes. Okay. So let us.
Actually, na your slide is moving, but your voice is not coming at it.
Yeah, that was a network issue. So yeah, I had to disconnect and reconnect. I thought switching over to a wired connection would reduce those problems. Last week there were no issues, but well, turns out even that is only limited. So yeah, so essentially what I was asking is, In how many directions are the electrons confined in this geometry? They can move freely in this direction. Can they move freely along the y direction?
X and Y. Mm,
They can't, because this length
there
is
is
only 6
confinement.
nanometers, right?
Hmm.
So there is confinement along the y direction.
Yes,
The
sir.
z direction, we will assume that it is large enough. So z direction also there is no confinement. So typically EXZ is continuous, EY is discrete. And similarly, for the case of a bulk MOSFET also, what as we just saw, the inversion layer is thick around 8 nanometers. That is along the y direction. But along the X and Z direction, there is no confinement, because bulk MOSFETs have a very long channel, right?
Yes, sir.
So even there also, the picture is the same. Confinement only happens along one direction, and the other two directions are relatively free. Okay.
But it will be large in the short channel effect.
Yes, of
The
course.
effects.
But we are not considering ourselves with that right now. What is more important is what happens in the case where we have this kind of a device. Now there is a very thin layer of silicon pressed on, two layers of silicon
Yes.
dioxide, correct?
Hmm.
So now along one direction, the silicon is compressed. In two directions, the silicon is free to move, right?
Yes, sir.
So what essentially happens is, because of that confinement, like if you remember the old band diagrams, like the isoenergy surfaces and stuff that we used to draw, along two directions, okay, the x and z directions, nothing will happen to the band structure. Whereas because of the confinement, the
Hmm.
y bands will kind of change, they will get distorted.
Okay, sir.
Okay, so because of that, what will essentially happen is, like previously, when we were talking about the silicon band structure, we understood that every energy level that I draw can be present in any one of these six directions in the k space of silicon. But now there are two distinct k spaces. There is the xz k space, and then there is the yk space. So corresponding to the xz k space, I will have the blue lines. Corresponding to the yk space, I will have the red lines. Okay. So now, because of that, what will essentially happen is that the effective mass along the y lobes will change. So this is where we are discussing the formation of subprimes. Subbands. So now there are two subbands: the primed subband corresponding to the direction of confinement or strain, and the unprimed subband, that is the unstrained region. So the unstrained region is the xz axis. The strained region is the y axis. Okay, so this will lead to the formation of like a staggered energy level configuration. In the lecture, this will be described in greater detail. I'm just giving you a rough idea.
Yes, sir.
And because of that, there will be two effective masses. There will be a transverse effective mass, there will be a longitudinal effective mass.
Okay.
And due to that, wait, that has not been covered here. Okay, yeah, that will, no, but that should be here. Should definitely be here. Uh, no, go on. But, 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 okay, something is not right. Yeah, let me just, you can see the course page, right? Kamal, can you see the course page?
Yes, sir.
Good. So, yeah, these are the same slides. These are the very same slides. I mean, of course they are. I took it from here. But the questions. So yeah, now I will just quickly browse through the questions. So as you can see, you are supposed to calculate the inversion layer thickness, find the inversion potential,
Sure.
There is a question on the body coefficient. There is a question on high K dielectrics. That is why I said your question is a very good question.
Yes, sir.
Now, there is a thing about like minimum length for preventing drain effects. So find out what to use. And then there are some theory concepts.
Yes,
Oh
sir.
God. So somebody. So yeah, there is a question on total effective mass.
Hmm.
Okay. Okay. So I will do this. I will do this part because that is important. With that, we will end today's. Yeah, and then I will take 5 minutes to show you some of the papers, and then we will, end today's discussion. So the last thing is total effective mass. Effective mass. Yeah, because there is a question and that thing is not present in these slides. Just occurred to me. So now what we have is we have the three-axis system. So over here, I have my strained, like, uh, I have the uh, strained. So those I will draw in blue. Okay, and the remaining I will draw in black. Uh, oh, I just said I will draw it in blue. Yeah. So these are the, yes, these are ellipsoids. Just assume that these are ellipsoids. Uh, and so these are the unstrained ones. Okay. And I have these ones over here. So the effective mass depends on the curvature of these uh, bands, correct? Like, do you remember? Okay, wait, let me just try to make this as neat as possible. Am I audible, Kamal?
Yes, sir.
So what I was saying is the, yes. So I have one lobe over here. I have another lobe over here. So these are the isoenergy surfaces for the silicon band structure. And I will have similarly one along this direction. Similarly one along this direction. Yeah, these will all be like symmetrically placed around the axis. Yeah. Yes. And so these are the strained ones. So let me just label the axis X, Y, and Z. So the blue line and I have a black line. So the blue line corresponds to the strained band or the strained subband, and this corresponds to the unstrained subband. Okay, so now essentially, which direction is the electron moving from the source to drain?
Sir, unstrained.
Yes, so they are moving in the XZ direction. Okay, so these are called the longitudinal. Uh, yes, these are called the longitudinal bands. Okay, these are longitudinal. Okay, This is called transverse. That is perpendicular to.
Yes, sir. Perpendicular to that channel.
Okay. So now there are two lobes here. Now, because of the straining, what will happen is this will have a different effective mass. This will have an M star transverse, and these four will have an M star longitudinal.
Okay.
Now, there are four bands with longitudinal effective mass and two bands with transverse effective mass. So, how do we find out what the average effective mass is? We find the average effective mass by taking the harmonic mean. So, 1 over like average effective mass, average is given by 4 divided by m star longitudinal plus 2 divided by m star transpose. So this is the formula. Maybe in the next week's slides, this thing will show up in greater detail. Okay.
Yes, sir.
So yeah, so that is the idea. So that is the formula you will need for, yeah, now I've almost kind of solved that question. So yeah, you're welcome. And for like whoever is looking at the slides, yeah, so that is effectively one question answered in your assignment.
Sir, are you looking some different page?
No, no.
Same this whiteboard, na?
Yes, yes, I'm in the whiteboard only.
Yes, sir.
No, like this is the question. Total effective mass.
Yeah, I thought you are thinking of these questions.
No, I'm thinking of these questions, but that is the thing. I don't want to discuss the exact answers to these questions. But
Right,
you
sir.
need a formula for this, and that formula was not present in the slides, so I've given that to you.
Yes, sir.
The numericals required for everything else has been given in the white slides. I cannot do more than that. And the concepts required for everything else I have discussed. So
Yes, sir.
now, yeah, I know we have kind of overshot the thing, but please let me take 5 minutes since you are the person who asked for it. I mean, the people who are watching this online are free to turn off the video right now. But again, for everyone's benefit, let me just open something. Open up this. Let me just. Oh, I was on the same window. Yeah, just 1 second. So this will be yes. Why are you? Come on. Yeah. Yes. So yeah, now these are three articles slash papers that I found. So this is a slightly old review article, which essentially talks about strain devices. So the
Please.
primary effect of strain is, so as you can see here, I'll tell you just one more thing based on what we've written in the whiteboard. So see, uh, what this
Please,
essentially does is,
like share.
oh, I
Yeah.
have not shared. Oh, sorry. Yes. Thank you. Uh, yeah, apologies, I forgot. Uh, yes. So, yeah, before going there, now can you quickly guess what will happen if uh, MT were to become larger?
Oh, it's like stopped, sir. You are presenting your screen,
Huh?
but
Yes.
it's stopped over there.
Okay. Now can you see the window?
Yes, sir. That one is coming. Just It's written there you are presenting your screen and it's stopped.
Okay, so there is some network issue again
Okay.
obstructing us. Let me try again. Like, has the sharing stopped now?
Yes, sir.
Okay, so let me share again. Okay, so can you see the whiteboard?
Yes, sir.
So can you tell me what will happen to M effective average if MT were to increase? Like, see, assume that initially MT was equal to ML. Then what will happen? M average will be ML by 6, correct?
Hmm.
Right? Like, I mean, it's just the reciprocal, correct?
M transfers M longitudinal, na? You are.
Like, assume initially that M transfers and M longitudinal are equal.
Yes, sir.
In that case, M average will be whatever M longitudinal divided by 6, correct?
Yes, sir.
Now, what will happen if M transpose in this formula is larger than ML?
Larger than ML.
Hmm. Like, let us say M transpose tends to infinity. What will happen to M average? It will become ML by 4, correct?
Yes, sir.
If M
This is
transpose tends to infinity, this term
clarified.
will vanish.
Yes, sir.
So from ml by 6, my effective mass has increased to ml by 4.
Hmm.
But if M transpose is smaller than ml, what will happen?
Infinite.
No. If it is, if it becomes smaller and smaller, and yes, if it becomes smaller and smaller, 1 upon M average will increase. That
Yes, sir.
implies M average will reduce. Is that clear?
Sir, if you are telling like M transpose star is getting
Yes.
smaller and smaller than 2 upon something like infinity.
No, no, don't
So
take it
the
to
response.
0.
Okay.
Like, so 2 upon that will be larger. And
Okay.
and since that larger number is inverse of the average effective mass,
Hmm.
the average effective mass will be a smaller number, correct?
Yes, sir. Hmm.
So if MT becomes smaller, average mass becomes smaller. If MT becomes larger, average mass becomes larger.
Okay.
Okay. So essentially, by introducing the strain, we can change the effective mass, and the effective mass contributes to the mobility of the electron. In our old analysis. So that is essentially what this paper talks about. So over here, we will get higher carrier mobilities by inducing strain.
That's good.
So this article covers like different kinds of methods of applying strain. So these are uniaxial like stresses and strains. So this is for CMOS devices. So essentially we deposit a layer of what is called tensile nitride or compressive, like we deposit it in a particular fashion so that the silicon dioxide and or any kind of substrate that you use here, in this case they are using silicon and silicon germanium. So lattice strains will get introduced because of this nitride layer on top of it,
Okay.
and because of that, and so these are the several geometries for uniaxial stresses and strains. We use a deposit like this kind of a geometry. For biaxial, we deposit a ring, essentially.
Hmm.
Okay, and because of that, what happens? What will essentially happen is that the band structure will get distorted like this.
Yes, sir.
So as you can see here, see there are red lines and yellow lines. These lobes are all changing.
Hmm.
So yeah, so this is what we have been discussing there. So the same thing is shown here. So because of this distortion of the band structure, we will have light electrons and holes emerging in the system. And the light electrons and holes, so as you can see, there are the different energy ladders here, primed ladders, unprimed ladders. So this is 001 for silicon MOSFETs. This is 110 things. So there is band splitting caused by electric field confinement and band splitting caused by strain and electric field. So all of those are shown here. Okay. And because of that, there is this phenomenon known as band warping, and band warping changes the mobility. So this article describes all of those things in some detail. I will share. I don't know if I'm allowed to share these things. I will maybe share the links of these things. You can try to download them. Like these are all open access. None of these were restricted. I just
Okay.
got these off of Google Scholar. So
Yes,
you
sir.
should also be able to download them. Okay. So I will share the links of these things. So as you can see, this is
Stress.
mobility enhancement over here, and several of these things are studied here. So similarly, there is another paper which is much more recent. Here, these people are talking about. So this is what 2020, yeah. Uh, by changing the doping profile. So by introducing what is known as Gaussian doping in a silicon on insulator MOSFET, this is a single gate MOSFET. So these people have shown how the electric field in the channel varies, how the drain voltage. Please don't. Yeah. So how the
Like stress.
temperature versus the drain voltage varies, and all of these are analyzed. And of course, they have some conclusions based on. So DIBL is also analyzed. So this is the structure they are proposing. Seems like it has the lowest DIBL.
Yes, sir.
Okay, and the floating body effect, which is essentially the body effect that we studied. So the body effect is also analyzed here between all of these. So you can see all of these graphs and how they are varying. And that should kind of give you an idea as to how these different quantities affect these parameters. So that is why in this course we are focusing on defining and characterizing these parameters, so that when you read a paper like this, you will understand what is happening, or at least what they are trying to communicate.
Yes, sir.
Similarly, this paper talks about this is, I think, still recent. I think this is from 2 years ago. Yeah, this is from 2 years ago. This is from 2021. So here they are proposing. So this is a review article. Here they are discussing in detail about multi-gate devices. So these
Fabrication.
are, yes. No, I mean, they are. I don't know if they've gone into the fabrication, but they have definitely talked about different multi-gate configurations and their associated parameters. So here you have a nice list of the DIBLs, variation with respect to gate lengths,
Yes, sir.
different, and it also gives details about the different people who have manufactured it. So these are the Intel IEDM devices. These are certain 13 nanometer Toshiba FinFETs. These are the IBM ETSOIs. So you'll see all of these things here, and there are comparisons between these things, and well, turns out there is some comments on the fabrication methods also. So this is for multi-gate devices. And so again, all of those things are discussed, and the limitations like self-heating effects and some other further limitations are also discussed here. Certain parameters for that are also shown. So you can again read papers like this, and based on what has been discussed in this course, you will be able to understand many of the things that are discussed here in better detail. So, I
Okay.
mean, as you can see, the things that we have discussed there show up here. So I can at least argue that the course content discussed is relevant based on state of the art research. So I
Yes, sir.
hope that kind of answers the question that you asked a few weeks ago
Yes, sir.
regarding papers and research work.
And sir, one thing more, like
Yes,
in this, all this, it is related with like MOSFET and short channel effects, like that.
yes,
So my question is like that, sir, for density of states.
uh huh,
For density of states, generally they are showing like energy and with respect to in x-axis, showing like
yes.
some negative and positive value. So some are telling like that if we are getting a higher peaks of energy value, na, then this device is good, and like that, sir. So
Higher peaks or
If
like what do you mean?
higher peaks of energy, sir.
For density of states.
Yes, sir. In density of states. If you will permit, na sir, then can I show you in the next week with some
Yes,
papers?
show me in the next week, and then I will, yeah, you can present in the next week, and
Yes,
I
sir.
will tell you what it is. By
No,
all
no.
means,
I will ask you some like what
sure,
they are.
sure. By all means, I welcome it. I
Yes,
mean, that has been my aim from the beginning. Like I want to discuss things rather than just talk about what is covered and solve problems.
yes, sir.
Please do. Okay.
Yeah.
Yeah. All right.
Thank you so much, sir, for this.
Yeah, so I think with that we can end this week's session. Yeah, it has been like kind of extended. We've almost gone on for 2.5 hours. So thank you for sticking around, and also to Ichanshu, but yeah, he
Thank you
wasn't
to
able
you,
to
sir. Actually, you are a
stay
student
on.
here, and that's why we have to wait to listen.
So yeah, so with that we can end today's session. We'll meet again next week, same time.
Thank you,
So yeah, I am ending the meeting. Yes.
sir. Yeah.
Bye.